The lecture today is going to be about limits at infinity. We are going to go through the list of 5-6 topics I've mentioned here. First item is the issue of tails of a function. When we are studying a function, we want to know what happens to that function far to the right and far to the left. So there are two tails to look at. One is the right tail and one is the left tail of a function. So if you have a function, it behaves certain way all the way to the left and certain other way far to the right. We are going to have two tails to look at. One is this left tail, and then one all the way here is going to be the right tail of the function. So all the discussion today is about this description of properties of these tails. Infinite limits, that is a topic we are going to see first. If the function escapes all the way to infinity or to minus infinity, we'll be talking about infinite limits. As opposed to what? Well, one alternative is oscillatory behavior. A function could keep oscillating as it goes to the right or left. That oscillation could be bounded or could be unbounded. Bounded means stays within bounds. Unbounded means, well, it gets larger and larger. For example, if you have a function behaving like that, as if it moves to the right. The one item that we are most interested in this section is the horizontal asymptotes. Many of the functions we are investigating them for the possibility of a horizontal asymptote. That means the function, when it reaches its tail, the tail acts more or less like a horizontal line. We are interested in knowing which functions behave like this. In engineering, a straight horizontal line, left or right, indicate that something stabilized. It doesn't go either too high or too low, but stays close to a certain straight line or horizontal line, which we call a horizontal asymptote, and we are going to abbreviate to HA. Well, we are going to have a list of examples drawn from typical functions we are going to study: rational functions, radical functions, a couple of exponentials and inverse trig functions might be mentioned. And if we have time, we are going to take a look at somewhat technical definition or the precise definition of what any of these things mean. Precise definition. So that is that, if you remember that epsilon delta definition we had, there is a version of those definitions that's applicable here. Okay, let's go and take a more detailed look at these items one at a time. So first, description of tails. We said tail of a function is the behavior far from behavior at far right or far left. Far right means the behavior as x goes to plus infinity. Far left means the behavior as x goes to minus infinity. Well, there are different types of tails that we want to investigate. What kind of tails could we have? Let's go look at some very basic functions you have seen many times in your algebra classes. What's a function you see very often? Well, straight line is a function you see very often. Well, we are going to refer to this section as the right tail of it, and this section as the left tail of it. Here you see that the function is going on straight, so left and right. There is nothing strange going on there. It's all familiar behavior. Now let's take a look at some other functions you have seen. you have seen parabolas. We want to know far to the right, how does it look like? We want to have some description of this. So that's the right tail, and here is a left tail of the function. So in any description of a function or graph of a function, we have the business of the issue of describing how does it look far from the origin and how does it look in the neighborhood of origin. These are so-called asymptotic behaviors or long-term behaviors. So in your physics or science classes, they are going to refer to this as a long-term behavior. Engineering classes might refer to it by some other terminology. Okay, here how do we describe it? We say the description for this is going to say as x goes to infinity, as x goes to infinity, that means as we go far to the right, y also goes to infinity. How about here? How do we describe it here? So as we march to the left, we describe it as x goes to minus infinity. What happens to the y? Well, this function, in this function, y goes to plus infinity again. Here, when x goes to plus infinity, meaning we go all the way to the right, the function pulls all the way up, so y goes to plus infinity. Here, when x goes to minus infinity, the function goes also to minus infinity. So one important thing is to find out how does the tail behavior look. These kind of situations where one of these goes to infinity, so does the other one. These are referred to as infinite limits. So infinite limits. Any of the combination of these things that you have seen refer to infinite limits. So if x goes to infinity, it so happens that y also goes to infinity. That's an infinite limit. That is characterized by a picture where the right tail is here. If you have x going to infinity, y going to minus infinity, you are dealing with a function whose behavior perhaps is like this, going all the way down, or perhaps with a different inflection as it's going down. Another item to look at is on the left tail. If x goes to minus infinity and y goes to plus infinity, which quadrant are we going to be in now? Remember, x going to minus infinity means going to the left, y going to plus infinity means we are going up. So here's a description of the the left tail of the function. And finally, if x goes to minus infinity, y also goes to minus infinity. It means you're dealing with a function where the left tail perhaps is somewhere around here. Now, there are other possibilities here. I don't want to mislead anybody, so let's go ahead and draw the other possibility as well. It could be that the function went to infinity like this, or went to infinity here like this, or here perhaps bent this way and went, or this one bent in this style and went. So long as you are in the correct quadrant, that would be okay. So that's infinite limits. How about oscillatory behavior? Sometimes, we were talking about types of tails. This is one type of a tail. Another type of a tail is something that shows an oscillatory behavior. Okay, oscillatory behavior, there are many types. Just to be brief, could be that as a function goes to the right, it acts like this, like a sine or a cosine function. If the amplitude of oscillation stays within certain numbers, we are going to call it bounded oscillation. Bounded oscillation means you can put a ceiling on top of it, you can put a floor below it, and they are not going to break through these. You can bound them. Another type of oscillatory behavior is when you have unbounded oscillations. So unbounded oscillations will be something that perhaps behave like this. A couple of years you're going to look at such a system that exhibit this kind of a behavior. The function keeps growing and getting out of hand. So this is referred to as unbounded. Well, what is the item that interests us most is the issue of horizontal asymptotes. So that's a third type of a tail we are going to look at, and that is referred to as horizontal asymptote. That is a situation where the function, when it goes to far right or far left, it settles down to a straight line. So suppose here, if I'm looking at the function and this function has the following property, that there is a certain line on it that can be drawn for the function with the property that as the function goes far to the right, it comes very close to that line. So here's a simple case of a function coming close to a line. Here's a graph of the function, here's our function, and here's the asymptote of that function. If it so happened that, for example, this was at height 3, that asymptote comes with an equation. The equation of the asymptote then is going to be written as y is equal to a certain number. So we are going to call this the horizontal asymptote of that function. Horizontal asymptote, I'm going to abbreviate it to HA. Okay, let's just go ahead and play with this picture. First get a hang of what the pictures look like, and then we are going to have lots of examples of how to actually do this from point of algebra. So we could have a function and say one asymptote for it. The function could have oscillated around this thing, something that you see very often in your physics or engineering labs. Something that is settling down behaves like that. So you could have oscillation around your asymptotes. Some of you from high school might have memorized that a function doesn't cross its asymptote. That's for vertical asymptote. There's no problem for horizontal asymptote being cut by the function. So here you obviously have a cut. Here are the cuts, and so on. So you could have infinitely many cuts. Some of the challenging problems you see later on, maybe the function cutting its asymptote just once. So here you might have an asymptote, and you could have a function just cutting once. If it comes once or many more times, we have something to pay attention to, and that's the issue of asymptote intercept. Asymptote is obviously an important feature of a function. If there is one and the function cuts its own asymptote, we want to know about it. So that is something that comes up in some exercises. You might keep that in mind. Of course, same kind of features could have happened on the left-hand side. So I could have had a function that is approaching its asymptote on the right or on the left. So this is a possibility that, say, the function on the right side, on the left side was acting like this, perhaps not cutting it at all. It is possible for a function to have two horizontal asymptotes. This one, let's draw a picture. We actually come across these things in our functions. Most notable is tangent inverse. So here is a function. It might have an asymptote on the right, perhaps another asymptote on the left. The function itself might have behaved like this. Pulling from one side of close to one asymptote to the other one, that would be an example of a double asymptote. So sometimes we refer to something as a right asymptote, another one as a left asymptote, meaning that the event happens on that particular side. It could have been that your picture goes the other way. The function might have come from left asymptote there to the right asymptote in this position. So these are all possibilities. Okay, we drew lots of pictures. We want to go ahead and actually work it from the point of view of algebra. It's always easy to see something and just talk about it, but when it comes to next item we are going to talk about is examples. Simplest example we have is the function y is equal to 1 over x. What happens to this as x goes to infinity? When x becomes very large, y becomes 0. Also, when x goes to minus infinity, y goes to 0. So best way to see that is to graph it, and I suggest that you stop this video, go ahead and graph this thing and come back and compare your graph with what I'm going to draw here. Now let's assume that you haven't seen this function at all. Well, that would be surprising if you haven't seen it, but let's assume that you haven't seen this function. If you haven't seen any of these functions, and then you are also stuck with this, perhaps forgetting some of the algebra that is related to this, how would you go ahead and answer the problem for yourself experimentally? Experimentally, well, you would need your calculator and patience. How do you go ahead and answer the question here? Well, you make a table for your x and y values. On your x values, suppose you want to discover the right tail. Easiest way to reach the right tail is to go through those numbers quickly. Here's a quick way of getting to the right. You just jump from 10 to 100 to 1,000 and so on. You make your way to plus infinity. And when x is 10, what is 1 over x? It's 0.1. What's 1 over 100? It's 0.01. What's 1 over 1,000? 0.001. And so on. As these numbers get larger and larger, these numbers go towards 0. We see they are all positive. So when x is 10, the height has already reduced to 1 over 10, which is 0.1. And then you go further down. It's going to be rather hard to draw because we have to go 100 units down, so we just imitate the behavior. This function is just going down. We understand from this behavior is simply stated the function is just dropping towards 0. What if I want to discover the situation at the left tail? At the left tail, then I have to make another table. I'll just go ahead and make it here. X and Y. I want to go far to the left, so I have to play with the negative numbers. -10, -100, -1000, and so on. I work my way to -infinity. Story is same as here, except all numbers are negative. 0.1, -0.01, -0.001, and we are marching towards 0. What does the picture look like on that side? Well, on that side the picture looks like this. What's the conclusion? The conclusion is that in this case x-axis itself has become our asymptote, that this is our asymptote both on the left and on the right. What's the equation of this dotted black line? The equation of that is y equal to 0. Y is equal to 0 is the equation of horizontal asymptote on both right and left. You can give more information by saying that this function is going to 0 from above. You remember how did we specify that? If you want to say it is going to 0 from above, you put a plus sign on top of it. Here you say y goes to 0 from above. It tells you this is descending. This one is like an airplane reaching cruising altitude. So here you can say y approaches to 0 from below, from negative numbers. So that would be like the icing on the cake. Not only you have specified where is the asymptote, you have also specified in which manner does the function come close to its asymptote. It can come from above, it can come from below. Some cases it could be oscillating, so you have to watch out for those. So this is the offshoot of all of this thing was that limit of 1 over x as x goes to infinity, either plus or minus infinity, is equal to 0. That tells us y equal to 0 is horizontal asymptote. So this was true for both plus or minus infinity. Similar reasoning can be given for other functions, like if I have y is equal to 1 over x squared. This one behaves rather similar to this. There are two differences. One is that this squaring makes it go to 0 faster, approaches asymptote faster. The other one is that squaring make it positive on both sides, so the graph of the function looks something like this. Here comes close to its asymptote, on the other side also comes close to its asymptote. So the graph of the function is this graph of y equal to 1 over x squared, and the horizontal asymptote again is y equal to 0. This is the horizontal asymptote for us. Okay, these were rather trivial examples. Now let's go ahead and open the discussion for something more interesting. Suppose my function, so here's a question, find horizontal asymptote of y is equal to, let's say, 2x minus 2 over 3x minus 5. Let me go ahead change this number so that our numbers do not collide. Here, let me say 4. So we have learned that we have to find the limit of this. Let's first go ahead and do it for the right. So we are going to find horizontal asymptote at right. Right means x going to plus infinity, and here is our function 2x minus 4 over 3x minus 5. Okay, we are going to go through many examples. Again, I remind you, whenever you are in doubt and you don't know what kind of algebra to do, you always can resort to your conceptual basis. What was it that you were looking for? You have been blessed with a good calculator. You can sit there and work it out. Better than that, you can just try to do it by hand and get a feel for what is really happening. Okay, so we are going beyond that. Let me say one more time. You always have this approach available to you. Just choose some x's and get your y's, and then figure it out in that way. You'll be asked for more than that, but that's always a default plan. It's better than nothing, let's say. Okay, the examples that I'm giving right now fall in the category of so-called rational function. Rational functions, you might have seen it in your college algebra classes. There is a basic approach to all of them, and here is the approach that gets us to the answer quickly. We go ahead, we divide numerator and denominator by the largest power we see in the denominator. What do I mean by that? Let me first write my fraction, prepare it. Then I'll go ahead and divide it by the largest power. Here's the largest power, this x. In the denominator, x to the power of 1, just divide by that. We will see in a moment what's the use of doing this. So x is going to infinity. Now remember, from basic arithmetic, if you have a fraction with several items on the numerator, one item in the denominator, you are always allowed to break it up. So it's a very simple basic algebra. Keep in mind something useful to know, very basic. Well, I can divide this thing term by term. That's what I mean. Term by term means you take 2x divided by x, so 2x over x, and the other one 4 over x, and 3x over x minus 5 over x. Again, x going to infinity. I go ahead and simplify my fraction. 2x over x is just 2. 4 over x, well, there isn't anything I can do to that. This one is 3, and then I have 5 over x. Now I'm going to use several limit laws that we have. One is this ratio, 4 over x. As x goes to infinity, this one goes to 0. Okay, so this goes to 0. This one, by similar reasoning, goes to 0 again. Remember, let me remind you, we just said 1 over x goes to 0. If you double that, same thing's going to happen. Double of 0 is still 0. 5 times that is still 0. So 1 divided by x goes to 0. That's why these guys go to 0. So numerator approaches 2 minus something, 3 minus something, and those things are going to 0. So numerator approaches 2, denominator approaches 3, and the whole thing approaches 2/3. So here's our answer. Horizontal asymptote on the right horizontal asymptote is y is equal to 2/3. Now we could have gone through this whole thing with a minus infinity instead of plus infinity. I could have used minus infinity all over this place, and the answer would be the same thing. So left horizontal asymptote is the same thing. Y is equal to 2/3. What does this mean? It means a crucial piece of the picture of this function has this thing in it. Y is equal to minus 2/3. Suppose, say if this was minus 1, say this is minus 2/3. The function we have considered here, 2x minus 4 divided by 3x minus 5, in some fashion comes close to this dotted line. Now in what fashion? We have to work harder to get that. Right now we are just focusing on finding this. The left tail or right tail of it is the same line. Okay, you do a few more exercises of this type. Let me move ahead and do something a little bit more advanced. Suppose the question is find right horizontal asymptote of y is equal to x minus radical x squared plus 2x plus let's say 5. Well, this is going to be significantly harder than the previous one. Again, the question is, what is the limit of that expression, whatever it is, x minus radical x squared plus 2x plus 5. Right means going to infinity, plus infinity. You want to find this limit. I'll be repeating myself, but let me remind you, we are going to dig into quite a bit of algebra. You always have that experimental approach available. That's in fact much more valuable than the algebra we are doing here. Just sit down and patiently do this. Make a table, see what happens, and try to guess what the answer is. Now let me go ahead and teach you from the point of algebra. What do we do here? We have to go through quite a bit of steps. We have difference of two items, one of them being in a radical. We remember the conjugate terms. We try to find this thing by multiplying with the conjugate. So I take this expression, write limit of, write what I had, x minus, see if I can fit all of this thing here. My writing a little bit too big now today. 2x plus 5. I have to multiply this. Maybe I go to smaller writing so it fits. This is what I had. I multiply this thing with its conjugate. What's a conjugate? Instead of subtraction, use addition. So I multiply with the sum of these two, and then I have to divide by the sum of these two. So what did I do? I didn't change anything. I just multiplied by 1 really. Limit is still being taken at the same point. So I go ahead, say equals to, remember, put the equal sign, limit of, well, what's the advantage of multiplying by conjugate? When you multiply x with x, well, you get x squared. When you multiply this radical with that radical, radical goes away. Remember, put the whole thing in parentheses. Denominator, I still have that whole mess, so there isn't anything I can do to it. I just leave it as it is. Next, numerator simplifies. Denominator stays as it is. Now I made that mistake of forgetting to write my limit. This type of problems, you might put the limit aside from the beginning, go through all the algebra, and at the very end bring the limit. But let's continue and use the same format everywhere. Okay, what we have done now is that we have converted an expression that was like this to that. It looks like we have jumped from frying pan into fire. We just made things a lot messier than it was. And we also made a mistake here. This was supposed to be parentheses. Okay, next term. I remember what I did with a ratio last time. What was the trick? To divide by something, to change both of them with respect to that. We try the same technique here. Suppose I want to divide numerator and denominator by something. What is it that would do the job? Well, in this case, it's not very hard to see. I'm going to divide by x. Notice this square root of x squared here. That's also about the same size as x. So the biggest power in the denominator really just x. So I go here. Maybe I change my color also, or yes, I write minus 2x minus 5. That is this expression with minus brought in, and denominator is x plus radical x squared plus 2x plus 5. I'm going to divide these two. I'm going to divide both of them by x. X is going to infinity. Next, I have to break it up just like the previous problem. So I write limit of x going to infinity of, this is minus 2x over x minus 5 over x. This is x over x plus that radical x squared plus 2x plus 5 over x. Now, for the next step of operation, well, what's the first step of operation? You can simplify this to minus 2. This we expect it to go to 0. This would simplify to 1. And this one, we are stuck to make sense of this. One part of the difficulty here is that we got some radical and some items outside of radical. So to see what to do with that, I just go back to something very basic from Algebra 1. If you have an expression, you want to force it to go inside the radical. What should you put inside radical? What should I put here? Obviously a squared. Just be careful, this is true if your number is positive. So if you want to force something to go inside the radical and that item is positive, just square it and put a radical on top of it. But what's the use of that here? The use of it is if I have radical x squared plus 2x plus 5 divided by x, and for some reason I like to see x inside this radical, I make one big radical. Numerator is just what it was before. Instead of this x, I put the x squared in the radical. Okay, so maybe I just for the sake of making more brief, let me see if I can so now I can break it apart. X squared over x squared, 2x over x squared, 5 over x squared. So here I write this is equal to the limit of minus 2x over x is just minus 2. It's minus 5 over x. X over x is just 1. This radical is just that. X squared over x is just 1. 2x over x squared is 2 over x. 5 over x squared is just itself, 5 over x squared. X is still going to infinity. Next, well, when x goes to infinity, what happens? This goes to 0, this goes to 0, this goes to 0. Square root of 1, what is that? I hope you do take it out. It becomes 1. I get from numerator, I'm left with minus 2. Denominator, I got 1 plus 1. It's minus 2 over 2. The answer is minus 1. Okay, so we went through quite a bit to find out. So we started from here. We want right horizontal asymptote of this function. First thing was difference of two items. One of them a radical. We multiplied by the conjugate. We simplified, divided by the power of x. To move that power of x inside the radical, we were careful to see what steps to take here. We broke it apart. Let the limit of all these items with the power of x in the denominator go to 0 and see what is left. And here is what is left out of that. So what's the final answer? A right horizontal asymptote is, how do we write the answer? We write y is equal to minus 1. What does that mean? It means in the picture of that rather complicated looking function, if you want to know where is it going to be sitting, we will have this horizontal asymptote, and the graph of the function come close to this blue line when we go far to the right. Now, does it come from above or does it come from below? Maybe I'll take a look at that function again, and let me see if you can guess an easy way of coming to this answer, bypassing a lot of stuff we have done, and also discovering if it is going to come to this from above or from below. So here is your function, and here is the horizontal asymptote of it. Two questions. Was it possible to see this without going through all that mess? And second question, is it possible to see if we are going to come close to it from above, or do we come close to this blue line from below? I'll let me give you a hint and let me leave it to you. What is it that you can do to this expression you have learned in Algebra 1 that makes it a little bit friendlier? Let me see. Let me put a 2 here. Did that ring a bell? Maybe we want to pause for a moment and come back. Well, this is really x plus 1 squared, and then you have some item left over 4. That one was called completion of squares in your Algebra 2. You used it for other purposes, but your idea is the same. Now, two things. When x goes to infinity, you're dealing with large numbers here. X plus 1 squared, you can think about it as the major component, and this 4 as a tiny amount that could be ignored in comparison to this huge number here. But if you ignore 4, what's going to be left? You're left with square root of x plus 1 squared, which when you simplify is just x plus 1. And all you have is x minus x plus 1, which is what? Which is minus 1. Well, that's the reasoning why you're settling down to minus 1. That infinity and that infinity will be in a tug of war, and the result of that tug of war is that they settle down to minus 1. Next question. Are we going to be above or below? Let me leave that for you for figuring out if you're going to be above or below. This 4 here is a crucial component. Think about it. If I want to include that as a tiny bit here inside this radical, where would it send me? Would it send me up here or down here? So think about it and come back. Okay, we want to go ahead through a couple of other examples. Some of these we have seen, so I'll be quick. Y is equal to 2 to the power of x. Question is, what is the horizontal asymptote of this? And is it on the right or left? We have seen exponentials very often. So where is it? On the right or left? 2 to the x, when x is a large negative number, comes close to 0 very quickly. So this is 2 to the x. This is the horizontal asymptote of it. Here is on the left. So it has a left horizontal asymptote. What's the equation of horizontal asymptote? Which is y equal to 0. We are simply saying that this purple line come close to the green one. So that's a very simple example of exponential. Just keep in mind that other exponentials are like that too. If you have y is equal to exponential of x, the picture is very similar. Use a different color. So here exponential of x, so it has a left horizontal asymptote, same location, y equal to 0. They are coming close to each other. What if I had the exponential of minus x? Exponential of minus x just flips the picture to the right, and now our graph is going to look like this. So now we are going to have a right horizontal asymptote. Again, equation of the asymptote is y equal to 0. That is talking about this line. Maybe one example from trigonometric functions. Trig functions themselves don't have a horizontal asymptote. Okay, so for example, if you take y is equal to sine of x, it doesn't settle down to anything. It just oscillates forever, and its oscillation is bounded. So this one is just going to behave like a wave that goes on forever. And so it has no horizontal asymptote. It has bounded oscillations. Well, is there anything there that has an asymptote? Yes, there are functions. Here, most important function is y is equal to tangent inverse of x. If you remember your trigonometry, you remember that. Otherwise, it's a couple of lectures by itself. Maybe you want to go and take a look at the review from trigonometry and take a look at these functions. I just quickly go ahead and graph the function for you. Tangent inverse of x. What is that? Maybe we can do a just 2-minute review here. That's an angle whose tangent is x. The angle whose tangent is equal to x. Well, so if I ask you what's a tangent inverse of 100, what would you say? What's an angle whose tangent is equal to 100? Well, what kind of angles have a very large tangent? If you remember that, that would be good. What angles have large tangent? If you come close to pi over 2 or 90 degrees, tangent goes to infinity. So tangent inverse of infinity is really pi over 2. So the graph of tangent inverse is going to have, it's the first example, you have two, it has two horizontal asymptotes, one at plus pi over 2, one at minus pi over 2, and the graph of it looks like this. If I can draw it. That's how it looks like. This is tangent inverse of x. Once again, if you are good with your trigonometry, you should remember that. If not, you might want to put this example aside, but that's a red flag. You have to go and review your trigonometry, make sure you are on solid foundation on that, and come back so that you can enjoy the chapters that are coming up. Okay, these were several examples about behavior at infinities. Just to spend a couple of minutes on precise definitions. Again, this acts as an icing on the cake. We have done epsilon delta definitions before. We talked about this thing before also, but we wouldn't have that much time to allocate to that kind of a precise definition. Those of you going to mathematics later on, you are going to see this all over again. The rest of you want to just have an intuitive understanding of what is being said and then put it as a secondary reading. So what does it mean to say limit of a function as x approaches infinity is equal to some number L? First of all, if that happens, then right horizontal asymptote of the function would be y is equal to L. If this happens, then you talk about it by saying right horizontal asymptote of the function is y equal to L. But what does this itself mean? It means that for any given positive epsilon, there is a number let's call it n, such that f of x and the final destination L are within epsilon of each other whenever x has exceeded n. Okay, sorry for that interruption. We're coming back to this definition, precise definition of the limit at infinity. Let me go ahead and draw a picture and explain what these things mean. Perhaps one way to understand this is through the concept of tolerances. So here is my function. Here's the x-axis, my y-axis. Presumably I have a asymptote so that is y equal to L. That's the asymptote, and I have a function that comes close to it, perhaps our statement is that if you specify a certain tolerance or trap size, so we are going above and below our limit by some amount epsilon, given amount, so this is going to be L plus epsilon, this is going to be L minus epsilon. I'll have the statement is, if you specify certain epsilon for me, I have to specify certain n for you, such that if I pass that number, then I fall inside of that trap forever. In this picture, where do you think the minimal value of n gonna be? Maybe pause for a moment and come back and tell me where is smallest you can take for n to be. Do you see where it is? Here. In this picture, it looks like this is going to be my n, meaning I am going to be inside this trap if my x is chosen to be here. So I say if x is here, if x is chosen from these numbers, my y is trapped between these two orange lines. My y is in this blue line, it's trapped inside, so if its distance from the ultimate destination, this green line, is going to be for sure less than epsilon. So this first cut was not applicable. It looks like this is the n in that particular problem. So that is the meaning of f of x approaching L as x goes to plus infinity. Similar definition exists for minus infinity, similar definition, somewhat similar for infinite limits. I let you go ahead and read that from text itself. You go ahead and do the exercise of this section. Good luck and